It's a great pleasure to welcome everyone to the World Science Festival, which, in case you don't know about it, is an event that we hold each year in New York where we bring audiences from around the world to experience science in a new way. And one of the things that we love to do is to push the boundaries of different disciplines, bring together art and science and education, kind of collide them all together and see what pops out of it. And this event is right in the sweet spot of that way of thinking about things because we're all here for what I like to think of as a kind of experiment in education, an experiment in virtual reality. What we're going to do is I'm going to, in just a moment, join you in the virtual world, and we're going to explore some pretty cool ideas, unification, relativity, a little bit of quantum mechanics. But then we're going to jump into an idea that's at the heart of these ideas, which has to do with extra dimensions of space, hyperspace. And part of the point of this experiment is to get a sense of how well you can absorb ideas when you don't just see them with flat animation on a screen like in a television documentary, but you actually get to play with it, to build it, to explore with it. So we are all going to together build a hypercube, a tesseract, be able to play with it, rotate it, throw it around between different members of the audience, and in that way gain what I hope will be a deeper intuition about some pretty strange ideas, these ideas of extra dimensions of space. All right, that's what we're going to do. In just a second, I'm going to join you in the virtual world, and we'll take off and explore some pretty wild ideas. Again, welcome to the World Science Festival. Hello, everybody. Welcome again to the World Science Festival. It is great to see all these avatars from all over the world with us here today. A couple quick things before we jump into this little VR experiment as I was describing it. If you take your device and you point it at any other member of the audience and you pull the trigger, you will be able to see what country they're from. So if you start to zap people with your little laser, you'll get a feel for the number of different countries that are with here, about 13 countries, 18 VR centers from around the world. And again, as far as the controls go, you'll see some of you have already begun. There are objects in your console that you can create, and you can take those objects and you can start to throw them through space. I'm already starting to feel like I'm back in an elementary school where I have to discipline the kids to stop throwing stuff around, but have a good time throwing stuff around. And what we're going to do, yeah, that's right. Someone just threw a black hole at me. That's very nice. I appreciate that. That's wonderful. And what we're going to do here today is explore some of the ideas that I just mentioned in relativity and in unified theories. And ultimately, we're going to build some stuff together, some four-dimensional hypercube, five-dimensional hypercube, and even a six-dimensional hypercube, and get a feel for some things that you simply cannot hold in the real world. So this is an experiment where we're going to get to manipulate things that simply don't exist in the three-dimensional world that we are familiar with. They can only be experienced in the realm of virtual reality, which makes this an exciting little experiment to undertake and see how it goes. Okay, so let's get to it. So the basic scientific ideas that drive this whole conversation have to do with trying to understand the fundamental laws of physics. And that's a story that goes all the way back even to late 1600s when Isaac Newton was trying to figure out how the force of gravity works. And just to get us all sort of on the same page, this is kind of science that I think many of us are familiar with, but what is it that Isaac Newton found? He found that every object in the universe, he found that it pulls on every other with a force. We call it the force of gravity, of course. And he wrote down a little equation that allows us to predict how objects will move under the force of gravity. So sort of just to get a feel for what that would be like, let's take a look at this little image right here where we have the sun exerting the force of gravity on the Earth, keeping the Earth in orbit, and using the little formula, the little equation that Newton wrote down, we can predict where these planets will be at any given moment. And the wonderful thing is, you look up into the night sky, and the planets are just where the equations say that they should be. And for that reason, people pretty much thought that Isaac Newton had figured out the force of gravity. And for a couple hundred years, that meant that nobody else was really working on this subject. They thought gravity was a done deal. But then in the early part of the 20th century, Albert Einstein comes along. He takes the stage of physics. And Einstein was the kind of thinker for whom there was no such thing as received wisdom, no such thing of ideas that had been worked out in an earlier age that we couldn't think about again. And when he began to think about the force of gravity, he realized that there was something desperately missing from the picture that Isaac Newton had given us. Because Newton never tells us how the force of gravity actually works. He simply gives us a formula that we can use to predict the motion of heavenly bodies, like some of the ones that we see floating around here right now. We see the planets moving around. And with the equation that Newton gave us, we can predict their motion and it all works. But that's not enough. We want to pull back the curtain and understand how the world works, not just treat it as a black box that can make predictions. And that's where Albert Einstein comes along, and he gives us a sparkling new way of thinking about how gravity actually works. How does the sun exert a pull on the Earth, which is so far away, through empty space? Einstein realizes that empty space can actually do something. It can warp and it can curve, and that way it exert a force, the force of gravity. So let me show you a little visual on that, and then we'll take ourselves into the actual virtual version of these ideas. So right here, this is a nice little image of Einstein's version of space. 3D space is what we're seeing here, and it's nice and flat, as you can see, when there is no matter present, empty space. But if I bring in the sun in this animation, the fabric warps. And similarly, if we were to look in the vicinity of the Earth, according to Einstein, also warps the environment. And then the moon is kept in orbit because it's rolling along a valley in the warped environment that the Earth creates. Look at that picture. This is Einstein's vision of how gravity is communicated from place to place, and the Earth is kept in orbit for the same reason. It's rolling along a valley in the curved environment that the sun creates. So this is the picture of how the force of gravity actually works. And now we are in a version of curved space. So you can look around and you can see how each of the heavenly bodies is having an impact on its surrounding. Each of the heavenly bodies is warping the environment. And then much as, a marble rolling on a curved rubber sheet will go in a curved trajectory. As you can look around, you see that the planets are going in interesting curved trajectories as they too are rolling around the curved environment that the sun creates. So that's the way in which the notion of curved environments, curved geometry, comes into our understanding of the physical universe. But then something very interesting happened. There's a Polish mathematician, this is now around 1919, who starts to think about Einstein's vision of gravity in terms of these warps and curves in the environment. And he says to himself, look, Einstein just got famous worldwide with this incredible idea that gravity is nothing but warps and curves in space. He says, I wonder if I can take that idea and push it a little further. Maybe the same notion applies not just to the force of gravity, maybe this notion applies to the other forces of nature, like the electromagnetic force. So this fella, his name is Theodore Kaluza, comes up with this idea that maybe other forces should represent in the laws of physics as the curvature of something. But that's where he got stuck, because what is it that could be curved? Einstein had already used up space, he'd already used up time in trying to describe gravity in terms of the curvature of the environment. There didn't seem to be anything left to curve that might be the substrate that would allow Kaluza to describe electromagnetism in terms of warps and curves. So here's what he says. He says, look, if Einstein's already used up 3 dimensions of space and 1 dimension of time, maybe there are more dimensions beyond the ones that we can see with the naked eye. We all know about left, right. We know about back, forth. We know about up, down, the 3 dimensions of common experience. Kaluza comes along and says, maybe there are other dimensions, higher dimensions beyond the 3 that we can experience, and maybe warps and curves in those extra dimensions. That's how we describe the other forces of nature. That's the idea. So let's now spend a little bit of time trying to get a feel for what in the world that could mean. What would it mean to have more than 3 dimensions? And the best way to get a feel for that is to actually start to build some higher dimensional objects. You guys are having fun creating some black holes and throwing things around of that sort. Now let's move on to a place where we can actually build some stuff. And I'm going to show you how to do it, and then no doubt many of you are going to run ahead to try to do this on your own. But let's go into this environment and take a look. All right, so we're going to start by building the simplest higher dimensional object. It's called a tesseract. It's a 4-dimensional version of a cube. It's also sometimes called a hypercube. And to do that, let me now bring up my little tool kit here, and it's going to go like this. So you see above me, I have one object, which is a little dot. A little dot is meant to represent a 0-dimensional object. No length, no width, and no height at all. So that's something of no dimensionality. Of course, it has some size here so we can see it. But it should mean that little dot is as small as it could possibly be. And what I'm going to do is I'm going to use that little dot to go from 0 dimensions to 1 dimension by taking a hold of it and bringing it over to here. And let's see if I can get that guy over. And if I put him in that location, I have now built a 1-dimensional object. And that 1-dimensional object has dots on either end, and it has a line extending between the 2 of them. And this is now a line. Simple. Everybody knows that that's 1-dimensional. But now let me use that by exactly the same procedure to build a 2-dimensional object. I'm going to take that line, and I'm going to move it up over here. And now I've built a square, a 2-dimensional object, simply by taking a 1-dimensional object and displacing it into the vertical direction, building a 2-dimensional object, a square. Now I'm going to follow the same exact procedure to build a 3-dimensional object, a cube. I take that square and I move it over itself. And now, as I do so, I can connect up all those lines. I have the familiar idea of a 3-dimensional cube. Notice something about this 3-dimensional cube. It's got 2-dimensional faces on opposite sides. So it's got 3 pairs of squares on its boundaries. Therefore, I've got 6 faces, 3 pairs of squares to yield this 3-dimensional object. And now we take the big leap is I now take this cube and I play the same game. I'm now displacing it relative to itself. So I got 2 copies of it. I'm connecting up all those pieces by lines. And now I have a 4-dimensional version of a cube. Let me just play around with this guy for you. By putting my controller inside, I can move this and you see that I have a beautiful example of a shape that you could not experience in the real three-dimensional world. But here in this virtual world, I have it right in front of me or right above my head as you see it, and I can move it all around, and I can rotate it in some interesting configurations like this, where it looks like the four-dimensional aspect of the object is kind of projected out, or I can put it in a configuration like this, where its four-dimensional quality becomes much more apparent. The way to think about this really is, imagine that this four-dimensional object is floating in a four-dimensional space that we don't have access to, and I'm shining a light on it. I'm casting a shadow in our three-dimensional world of a four-dimensional object. And much as shadows in everyday life, they can overlap, they can pass through each other. You know, if you and a friend, brother, sister are walking along in the sunshine, your shadows can cross over each other. You see that the shadow in our three-dimensional world, I mean, the shadow in the real world is two-dimensional, but in our virtual world here, I'm now looking at a shadow in a three-dimensional world, and you see that the various qualities of the shadow are crossing over, the edges are passing through each other, and so forth. So this hypercube, this tesseract, you can think of it now as having cubes on its boundary. And how many cubes are there? Well, you've got 4 pairs of cubes on its boundary. In terms of the total number of edges, we've got 16 edges here. And if I take this object and I just sort of let it fly off, you can see it's got this beautiful strange quality in the real world. Now, I see some of you have jumped ahead, but now let's do this for a 5-dimensional object. And this I can step through a little bit more quickly. You should feel free to go at your own pace if you'd like to, but same exact steps. I take my 0-dimensional point. I pull it over to make a 1-dimensional line that I have over here. I take my 1-dimensional line, I displace it to yield my 2-dimensional square. I take my 2-dimensional square, I displace it to make my 3-dimensional cube. I take my 3-dimensional cube, I displace it to make my 4-dimensional hypercube or my tesseract. And now I take my tesseract and I displace it relative to itself to yield a 5-dimensional hypercube, also the pentaract. And I can take this guy, and again, now you see the richness of all of the various tesseracts that are crossing over each other in this shadow version in our 3-dimensional world. And as you can see, you can really get a feel for how these different components relate to each other by slowly rotating it around, seeing how the shadow intersects, overlaps, and relates to itself as we rotate this 5-dimensional object. So now I can take this little guy and in fact, you guys can throw this among yourselves if you want. So I'm going to throw it to one of you guys. You can actually grab this if it comes near to you. I can grab one of yours, actually. And if it gets close, you can use your button. Here, I just grabbed somebody's. It was, but I'm going to take this and see if I can pull it into myself. And there we go. Thank you. All right, so this is 5D. What the heck? Let's go for 6D as long as the system won't crash. So you guys can do this as well. I'm now going to build a 6-dimensional object. Same exact idea. 0-dimensional to 1-dimensional line. Take my 1-dimensional line and I displace it to get my 2-dimensional square. 2-dimensional square, displace it to get my 3-dimensional cube. Take my 3-dimensional cube, displace it to get my 4-dimensional tesseract. Take my 4-dimensional tesseract, displace it, connect up all of the vertices to get my 5-dimensional pentaract. And now I take my 5-dimensional pentaract and I displace it to get my have lost it for a second. I think we're taxing the system at the moment, but it's all for a good scientific purpose. Good. Now I can take this guy, rotate my 6-dimensional object above my head. All of these 5-dimensional pentaract on the boundaries. So you've got 6 pairs of tenteracts on the boundary of the 6-dimensional object. Each of the tenteracts, of course, has 5 of the tesseract in pairs on its boundary, and each of the tesseracts, of course, has pairs of cubes on its boundary. So if I now take this beautiful object, throw it off into space, it waft away, and if someone wants to grab that before it drifts beyond reach, feel free to grab it. So that's 4-dimensional objects, 5-dimensional objects, and 6-dimensional objects. And now I'm just going to go on to describe how these objects actually come into our fundamental understanding of physics. But before I do that, let me see if there's a question or two which you all can ask by simply clicking that question. Any questions, I will open up a channel to actually hear you talk. No questions at all? Well, someone just threw us a hepteract at me, which is very nice. Let me just grab that and I'll throw it back to you. All right. Okay, so let me just grab this one here. Yeah, so whoever built this one, that's a very nice little specimen that you got right there. I'm gonna throw it to somebody over there. Someone grab that if you want. Very good. As it goes around the world. Okay, so what do we do with these ideas? Well, let me just show you how these now come into our understanding of physics. So I mentioned that our friend Kaluza came up with these ideas as a means of trying to describe the electromagnetic force. But immediately people questioned whether that was a sensible thing to do, because where are these dimensions in the real world? It's one thing to do mathematics and talk about higher dimensional spaces. It's another to talk about physics and how the world works. So the immediate question is, if you're going to introduce more dimensions than the 3 that we know about, where are they? And an answer to that question popped up in about 1926 by a guy named Oscar Klein, and here's what he found. I'll show you it in visual form. He basically found that dimensions can be big and obvious or small and hard to see. And to get that idea, take a look at this little visual right here. So we're looking right here. If you guys can see this, or maybe I should change scenes on this and do it in the next one here. Good, yeah, so that's a traffic cable, which is very skinny, hard to see that it has any thickness at all. But if you zoom in, and you take the perspective of little ants that are walking around, they're so tiny that they can not only walk along the cable, they can also walk around the cable, revealing, and this is the point, that the cable has a circular dimension wrapped around it. So the cable has a long dimension, easy for us to see, and a curled up direction. It's very hard for us to see. You have to be able to probe into the micro world to actually reveal that it exists. And that suggests that you can have big dimensions obvious, tiny dimensions that we might not know about. So maybe the extra dimensions required by these physical theories, maybe they're all around us, they're just too small for us to see. And indeed, there's a beautiful theory that no doubt some of you have heard of called string theory, which takes these ideas one beautiful step forward and imagines, as I'll show you, the following. So this is now an image, if you will, of space, environment all around us. And we're now going to go on a journey. We're going to go smaller and smaller and smaller. And according to these modern ideas, if we go small enough, we will encounter extra dimensions. These little circles are representing the extra dimensions. So if you have a little tiny microscopic ant walking around down there, the ant can not only walk in the dimensions that we all know about, but it can also walk around these curled up dimensions that we cannot see with the naked eye because they are just too tiny. And the idea is that if you take the mathematics of these theories seriously, the actual shape of the extra dimensions looks like this. These are known as Calabi-Yau manifolds. There are 6-dimensional spaces. That's why we were looking at 4, 5, and 6-dimensional hypercubes to give a feel for this. These are more complex, higher dimensional objects than the ones that we have built. But if these ideas are correct, this is what the extra dimensions of our universe might actually look like. So this, of course, is in animated form. Let's try to now experience that a little bit in the actual virtual world that we have around us. So here we are back in the curved environment of Einstein in the three-dimensional space. But now let's push this one step further and imagine that the extra dimensions are very small. So we're now going to go on a journey to a very tiny realm. We're now going smaller and smaller and smaller, yet smaller, even smaller. We're shrinking by factors of 10 every step of the way, and we're now all the way down at about 10 to the minus 33 centimeters, incredibly tiny. And you see the extra dimensional Calabi-Yau manifolds. So now each of you has a Calabi-Yau manifold in front of you, and much like the hypercubes that we all built, these extra dimensional spaces, they can, as they rotate, pass through themselves. They show shadows of themselves as they're going through it. And if these ideas are correct, the objects that we built together, the Tesseract and the Pentaract and the Heptaract, the 4, 5, and 6-dimensional spaces, they may actually have physical relevance, as these may actually represent how the extra dimensions of our world actually behave. So again, if these ideas are true, even where you are sitting right now in the real world, not in the virtual world, these extra dimensions would be all around you. As you move your hand, you're all sweeping your hands around using your controllers. Your hands would actually be sweeping around and around and around these extra dimensional spaces that are so tiny that we've never seen them, yet they're all around us. So again, you can take these guys and you can throw it from one country to another. So I just toss my Calabi-Yau manifold to somebody. I don't know what country this person is from, but there you go. And yes, these are these beautiful higher dimensional shapes which may actually have relevance to the world around us. And just to sort of finish up this discussion a little bit, let me just show you how the physical theories would look with these extra dimensional spaces. So let me give you an example here of a world in which we have these guys over here. So string theory, as I mentioned, is the theory in which these ideas really come to life in the modern way of thinking about physics. So what is string theory? So I'm going to illustrate by taking an object, a candle, could be anything at all. And just as we did with space, we dove into space. We're now going to dive into the candle. We're going smaller and smaller. We all pass through the molecules, atoms we all know about. But we're going to go even further. We're going to go into the atom itself. And inside the atom, many of you know that the neutrons have quarks inside of them, which you're seeing right now. Inside of the quarks is where the ideas of string theory emerge. This is the new hypothetical idea. There might be vibrating filaments deep in the heart of matter, and these little vibrating filaments are the heart of matter itself. So everything in the universe, according to the ideas of string theory, which are speculative and hypothetical, but mathematically quite beautiful and compelling, everything would be made up of these little tiny filaments. Little tiny things. And the way the extra dimensions come into the story is that if you think about how an object like a string vibrates, its environment affects it, much like the shape of a musical instrument affects how air vibrates within inside it. So let me give you that analogy right here. If I've got, say, a French horn, the vibrations of the air by the shape of the instrument, the twists and turns of the instrument. Similarly, if we replace this instrument by a Calabi-Yau manifold, these higher dimensional shapes, the strings that are vibrating in that environment, their vibrational patterns are affected by the shape of the higher dimensional space. So I'm going to bring in a couple of strings in a moment, vibrating in this environment, and you'll see the twists and the folds of the extra dimensional space affects how the strings vibrate. There you see it coming into view right here. And those different vibrational patterns correspond to the different physical properties of particles particles in the world around us. If a string is vibrating one way, it might be an electron. If a string is vibrating a different way, it might be a quark. And in that way, the extra dimensions affect the kinds of particles because it affects the kinds of vibrations that the strings can undergo. So these ideas are at the cutting edge of forefront research, but you see how they bring together the ideas of Einstein's curved space, as we see in the world around us right now, bringing the idea of extra dimensions of space, because string theory demands, the mathematics demands that there are extra dimensions of space. And then you see that the twists and turns in the geometry we explored in the simpler case of the 4, 5, and 6-dimensional hypercube, the geometry of the extra-dimensional space has a profound impact on the physics of the world around us. So if these ideas are true, this virtual world that we are inhabiting right now would actually be a model for the real world, but an aspect of the real world that we can't actually see with the naked eye or even experience, because it's not something that we're able to inhabit because we're just too big. If we were all born 10 to the minus 33 centimeters long, as opposed to the typical human scale, if we are born at that tiny scale, we'd be walking around that micro world, and if these ideas are correct, we'd be seeing those extra dimensions all the time. It would be second nature. But because we aren't born so small, we have to enter this virtual world to try to get a feel for how these extra-dimensional theories actually work. So that's most of what I wanted us to do, our higher dimensional exploration into hyperspace and these ideas of relativity and string theory. We have a little bit of time to have some conversation or questions if anybody has any, and if you do, try to hit that question mark. And I think I see one over here. Let's see. Do you have a question?
My question is mostly based on what is your relationship to the whole simulation of the universe, like the idea that we actually right now is living inside of a simulation of some sorts. Do you have any strong opinions one way or the other on that?
Yes, I mean, there's a very beautiful idea that really comes from a guy in its most refined form at Oxford named Nick Bostrom, which thinks that this virtual world that we are inhabiting right now, in some sense, is not really a metaphor. It's not really a model. The suggestion is that maybe life as we experience is nothing but a computer simulation. And the reason for this way of thinking is quite straightforward. As we get better at creating these virtual worlds, maybe we'll ultimately create one that will have its own inhabitants, that will be sentient conscious beings. And the way of determining the likelihood of that is to simply ask yourselves the following question: how hard is it to create a real flesh and blood, molecule and atom universe? That's pretty hard. No one's ever been able to create a second universe. But how hard is it to create a simulated universe? Well, if the software is available in the future to create simulated worlds with sentient beings, any kid in a garage can simply turn on that software and create universe after universe after universe, all inhabited with beings that have no idea that they are in a simulated world. So if you then ask yourselves, how many sentient conscious beings are real versus how many are simulated? Well, there's only one real universe, and there might be a gazillion simulated worlds, which means that there are so many more simulated conscious beings than there are real ones, which leads to the rational conclusion that if this is possible, that we are much more likely to really be in a simulation than to be in a real world. And if that's the case, then right now, we are in a simulated world, inhabiting a simulated world inside that simulation. Now, do I believe that? I can't say that I do. I have an open mind as this is a real possibility, but I'm not ready to buy into the possibility that life as we know it is taking place in a supercomputer in some teenage kid's garage in some strange future. But yes, it's an interesting possibility, and who knows, it just might be right. Other questions that anybody has? Is a question over there? Whoops. Thank you. Right over there. I'm trying to illuminate you, person with question, but there we go. Excellent.
Yeah, hello, Belarusky. Can you hear me?
Yes, I can. Hear you quite well.
Great. So my question is, if there is a possibility that we are also a projection from 4D or 5D or 6D space, how would we look like in that space? And is it possible that it is like that?
Yes. So if the ideas of string theory are correct, then indeed, fundamentally, the universe would have 10 or maybe even 11 dimensions, which would mean that every object that we normally think of as being three-dimensional, including our human bodies, would be existing in that higher dimensional space. So we would have a little bit of thickness in these extra dimensions that we currently are unaware of because we don't have the visual acuity, we don't have the resolution to actually measure it. Now, that's a strange idea in its own right, but let me go one step further. If the extra dimensions in string theory, which if the theory is correct, we imagine being really tiny, imagine those extra dimensions, those colorful Calabi-Yau shapes. Imagine they were to grow bigger and bigger and bigger so that they weren't microscopic. Then our bodies would really be floating in this higher dimensional realm. And that would be an environment where I don't think we would be able to survive. For instance, if you imagine a two-dimensional being on a flat piece of paper, we three-dimensional beings can look inside of a two-dimensional being. Stuff that's within, organs that are within a two-dimensional being could fall out of its skin. Similarly, all of our organs would be able to drift outside of our bodies if the higher dimensions were big enough to actually accept them. So it's hard to imagine life as we know it actually existing if those extra dimensions were big. If they're small, then their only impact on us is to give us a little thickness in those extra dimensions that we're currently not aware of. Very good question. Other questions from any other part of the world? Yeah, that's a beautiful hypercube, whoever just built that one. I can throw that one back to you. Any other questions over here? Is there one? Okay, yes. And where are you from? Can you hear me? All right, let's go to the next question over here then. I sort of feel like a radio talk show host who's just, oh, I gotta shut you down. Go ahead, can you, your question mark is still on. Do you have a question over there? Yeah, unfortunately, we are not getting your audio. And let me try this. Yes, go ahead. Where are you from?
I'm from Denmark right now. My question is more like to you right now. How does it feel to talk to so many people like right around the globe right now and teach so many people? Like, how does it feel to be a teacher in the next dimension of teaching? Or what you
yeah,
can
well,
call
exactly.
It?
Yeah, but like we said at the outset, it was really just a little experiment to see how this would go. But how wonderful is it that we're all here from more than a dozen different countries talking about ideas that are relevant and true for all of us, that we have equal access to and equal relevance from. So I can really imagine that this would be the imagination. It shouldn't matter what country you're from. Knowledge should be widely available. And to me, it's sort of a thrilling first step to taking education in a global direction. Absolutely. And I saw that there was another question somewhere in this environment. So if you want to hit your question mark again, I will try to bring you up. Yes, where are you from?
I'm from Los Angeles, California. Can you hear me?
Wow, yeah, that's really exotic. Los Angeles, California, fantastic.
So three things. What's the latest research on black holes? Do you think humans are going to populate another Earth-like planet? And what's the best way to get VR into public schools?
Well, you know, black holes, I'd say, are really, these days, on every physicist's mind who works on things like unified theory or gravity or general relativity. There's so much activity happening. For a long time, we thought we understood black holes. But in recent years, we've realized that the edge of a black hole, the so-called event horizon, I think we have a black hole behind me, yeah. So that black region, we thought we understood. It was a place where if you crossed over it, you could never come back. It was a place where time slowed down, infinitely slow right at the edge. But now we realize that when you put quantum mechanics into the story, things may be very different. The edge of a black hole may be what we call a firewall. It may be an incredibly hot realm where anything that crosses into the edge just gets burned up and all its information gets stored on the surface of the black hole. So these are ideas that are at the cutting edge of thinking, and I imagine in the next few years there's going to be revolutionary breakthroughs that are sparked by a lot of this thing, sparked by black holes. In terms of your second question, getting VR into the classroom, I think this has to happen. I mean, this is just a little test case, but imagine this is the tip of the iceberg. Imagine that when I'm teaching quantum mechanics, I can take kids right into the micro world and see quantum wave functions. Or when I'm teaching general theory of relativity, I take everybody right to the edge of a black hole. We would leave our pods or fly through space in our pods and experience time slowing down at the edge of a black hole. Or imagine I take us right back to the Big Bang and we all experience the expanding universe from a fraction of a second after the beginning. This kind of experience will completely transform the level of understanding. So that is the future. How to get there, that's a much more difficult policy question that probably will handle country by country or municipality by municipality. But yes, I think that's ultimately what's going to happen. Question over here? Yeah. Where are you from?
From the UK. Can you hear me?
Yes, I can.
I got a question regarding those multidimensional universes because, as you said, they're surrounding us, and I was just wondering, do we actually make an effect, or do we interact in some way that we don't even know with them? Is there any sort of way that they interact, they have an impact on us
Yes.
that we don't understand or know about?
Yes. No, that's all a very good question because, again, if these ideas are right, and I keep underscoring that because until you have observations, until you have experiment, these ideas are theoretical. But if they are correct, then these extra dimensions are all around us in the real world right now, and we are moving through them. Every day as we sweep around, we're actually taking these higher dimensional journeys. It's just that we return to our starting point so quickly because the extra dimensions are small that we don't realize that we took the journey at all. But yes, they do have an impact. So the example that I gave with the French horn is one thing to keep in mind. Your strings, making up your particles right now as they are vibrating, those little strings, they're vibrating not just in the big dimensions that we see with the naked eye. Your strings are vibrating into those tiny extra dimensions, and the shape of those extra dimensions are having an impact on the ways that your strings vibrate, which has an impact on the way your particles behave. So those extra dimensions are shaping almost everything about the world if those extra dimensions are actually with us, if they're actually there. And that makes this an incredibly exciting prospect that much of what we have found mysterious about the world, why the electron has its mass, why the quark behaves as it does, the answers to these questions may be found in the geometry of the extra dimension. So if you look around, many people have those Calabi manifolds floating in front of them. The geometry of those extra dimensions, and this, by the way, I should stress, is just one example of a Calabi shape that we showed you when it came up near your pod. There are many, many variations on that shape, therefore many variations on the kinds of physics that those shapes give rise to. So the future of physics, the future of understanding reality may boil down to the future of understanding these higher dimensional shapes. Before we wrap up this little experience. All right, I don't seem to see any other questions. Those are some quite wonderful ones that we had. So that concludes this little experiment exploring hyperspace and virtual reality. So thank you for participating. World Science Festival programs are online for any of you around the world who want to see the things that are happening in the next few days. And keep your eyes open as we push the boundaries of VR in an attempt to take education to the next level of understanding. Thank you very much.